My name is Chibuzo Nyagasi, and today I'm going to be talking about the life of a gas. The life of a gas, which is basically how gases act and how they behave and their properties, can be explained by the kinetic molecular theory, which studies the model behavior of a gas in a container and then allows us to understand how gases act and how they move, how they collide, and study a gas. The molecular theory was made for ideal gases, but it can also be used to explain real gases as well. The difference between ideal and real gases is that ideal gases obey all the gas laws. And we're going to find how gases behave and their energy, which is also tied to the temperature of the gas. Okay, and this molecular theory is based on 5 assumptions. And these 5 assumptions are also called the postulates of the kinetic molecular theory. The first assumption is that the gas is made up of particles with no defined volume but with a defined mass. You might begin to stop and be like, wait, how can something have a mass and not have a volume, right? But while you're stopping and having concern about that is true, gas molecules are so small that the space between one gas molecule and the next one is so large that it is safe to assume, that's why they're called assumptions, that they don't have a volume but they have a mass. So you're right in stopping and thinking that how can something have a mass and not have a volume? But with those assumptions that we make, it's safe to assume that they have no defined volume. The second assumption is that the gas molecules have no intermolecular attraction or repulsions. And that should kind of make sense because if this gas particle has some kind of attraction, you would have blobs of gas because they're all attracted to each other. And that kind of doesn't really make sense from even just thinking about it logically. And these gas particles, since they have no attraction, they behave independently of one another. So one gas particle A and gas particle B act like they don't see each other. There's no attraction to each other and they just move any direction they want to move. Which brings us to this assumption that says gas particles are in continuous random motion. So these particles, although they move continuously and randomly, but the particles are not at the same speed. We could say they have an average speed, which we call the root mean square velocity, but but all of them are constantly moving randomly. So they're just haphazardly moving and bouncing off the walls of the container, bouncing with each other, but they're constantly in a state of motion. The only way to get these gases to stop moving is at lowering the temperature to absolute zero, and at that point, there's no gas particle moving because it's absolute zero. That's the lowest temperature you could get. The collisions of these gas particles are completely elastic, and that means that the energy before collision is the same as the energy after collision. So if the gas A and gas B, gas particle A and gas particle B are moving, the energy before they collide individually and after they collide is the same. So no energy is lost. You can think about that, like how billiard balls collide. They collide with the energy. It's not the same energy because you hear the collision and some energy is lost as sound, but it's the closest thing we could, as scientists, it's the closest thing we could compare to the collisions of gas particles. That the speed before is the same as the speed after, and hence their kinetic energy is the same. Okay, the fifth assumption is that the average kinetic energy is the same for all gases at a given temperature, regardless of the identity of the gas. So what this means is that even though a gas might be a relatively heavy gas like oxygen and a light gas like helium, their average kinetic energy, if they have the same at the same temperature, their average kinetic energy is the same. So it doesn't matter if oxygen is a lot heavier than helium, their average kinetic energy must be the same because they're at the same temperature. And the definition of temperature, I think I said that before, is the average kinetic energy of a molecule. So by that definition, if their temperature is the same, their kinetic energy is the same. So it doesn't matter if it's a heavy or light gas. And another thing I'm going to talk about is diffusion. And that is the movement of gas molecules from a region of high concentration to a region of low concentration until it's equally distributed. And you can see this cartoon or not a cartoon, like a little picture down here. you can see hydrogen on one side and oxygen on the other side. And as I open that stopcock, you see that oxygen moves from the right to the left, that is from where it's highly concentrated to where it's lower concentrated. And the hydrogen does the opposite in direction. It goes from, well, it still does the high concentration to low concentration, but it's moving from the left to the right from this picture until they're both equally distributed on both sides. And diffusion is kind of tied to the speed of the particles, and logically that should make sense that the faster a particle is moving, the higher energy it has, the quicker it's going to diffuse, the quicker it's going to move from high concentration to low concentration. And that should really make sense. It's not really a difficult concept to understand. So gas molecule from high concentration to low concentration. You could also see that in cell membranes as well. When we're talking about gases, and gases can also freely diffuse through this lipid bilayer. You can see here that in our bodies, diffusion also happens. You can see that they're highly concentrated here, and over time, it moves from that high to low concentrated area until it's evenly distributed. So there's a zero concentration difference between both sides. So that diffusion is happening right now in your body. So that's pretty cool. Okay, another thing I'm going to talk about is diffusion. And diffusion is a process where gas particles escape from a container into a vacuum through a very small hole. And diffusion kind of has the same concept as diffusion, and because they're moving from a obviously high concentrated area to a lower concentrated area, because the vacuum is a very low concentration because there's nothing in the vacuum, and they're moving through a pinhole. I think that's like the only difference, because there's a pinhole there that kind of allows it to move a lot slower, but it's still the same concept, and they can also be explained by the same law, which I'm going to talk about real soon. It's also related to the root mean square velocity. And I said before, just think of that as simply as the speed of the particles, and it's basically pretty much the same thing as diffusion, besides there being a pinhole here, so it's easier to grasp. I'm going to talk about that law, and that law is called the Graham's law of diffusion. Some people call it the Graham's law of diffusion, but like I said, it's kind of like the same thing, so the law governs both topics. Okay, so Graham's law states that the rate of effusion or diffusion is inversely proportional to the square root of a molecular weight. And to understand that, there's this which shows that rate is inversely proportional to the square root of molecular weight. And if you think about that, that would make sense, because if you have a higher molecular weight gas, such as maybe oxygen, if you put a bigger number, 1 over a bigger number, it gives you a smaller number, which is a smaller rate. But if you have a small molecular weight for something like helium, you see that the 1 over a smaller number would give you a bigger rate. And that should make sense, because smaller molecules will travel faster than larger molecules, and they would have a faster rate of diffusion. And here you can see both, you could sort of combine the rate and molecular weight of gas 1 and gas 2 to give this combined equation. You can actually use this to solve problems relating to diffusion and Graham's law of diffusion of gases. So you could use this equation to solve problems. Maybe you're given the molecular weights and you're trying to find the rate, or you're given the rate and you're trying to find the molecular weight. So you can use this equation. It's very good in solving problems relating to diffusion. Okay, if that wasn't a clear enough explanation, I'm going to kind of explain how that law works. So we said that at a particular temperature, gases have the same kinetic energy, right? So here you can see the kinetic energy of gas 1 is equal to kinetic energy of gas 2. And well, M is the mass of gas 1, M1 is the mass of gas 1, and M2 is the gas of mass 2, right? And if you're looking at gas as a whole, you could, this might be for one gas particle, but if you look at the gas as a whole, the velocity of a whole bunch of gas particles can kind of be related to the diffusion rate. So I can choose to substitute the V1 as a diffusion rate if I'm talking about a container of gas. And if you change V1 to diffusion rate, you can see you get this half M1 rate 1 squared equals to half M2 rate 2 squared. And that is Graham's law. If you do some mathematical manipulation to this, you get this, which is the same as we saw as the previous slide. So that kind of explains Graham's law. And you can see that from if these are the same, if this mass is smaller, the velocity of this has to be bigger than the velocity of this to kind of balance it out for it to be equal. And that's Graham's law. It's basically saying that the faster a gas is, the lighter it is, or the slower a gas is, the heavier it is. And that's kind of easy to understand. The last thing I'm going to talk about is the mean free path, and it's the average distance a gas particle travels from one collision to the next. And to envision that, you can think of, say someone decides to open a can of rotten food there, and we have established the gases move really fast, but you don't really smell it immediately. Like some of these gases are so fast that they move about hundreds of meters per second. And someone opens that up, and you don't really smell it immediately, although it's moving that fast. And you might wonder why. Well, the thing is, these gas molecules are colliding with each other, so it's not just shooting straight at your nose, or it might be trying to go, but then it collides with another molecule, and then it goes the other way. So before it makes all of those collisions to actually meet you, it might actually take a couple of seconds for the particles to reach your nose, although it's moving at crazy fast speed. So the mean free path is basically a distance for of a gas molecule to hit another one. And it increases with decreasing pressure. And that shouldn't be hard to understand, because if you have a gas molecule in a container and they exert pressure in the container, and you take some of this particle out and replace them with there's more vacuum in, you take some of the gas particles out, right? So there's less gas particles in that container, and it's going to be harder for them to collide with each other because there's more space. It's going to be relatively harder for them to collide with each other because there's more space for them to move around. So you can see that with that low pressure, the mean free path, since it takes a longer time for them to collide, you're increasing the mean free path of the gas particles. And that's pretty much the explanation of mean free path. That is where I will stop this video. I hope you enjoyed it, and thank you for watching. Thanks.